Okay, right. Can you guys have a look at page 12 under your DC circuits worksheet? Okay, so I'm going to go through internal resistance, then maybe a bit of potential divider and some special questions for today. Right. So now, if you look at page 12, question 32, you have a cell of EMF E and internal resistance R that's connected to an external resistor as shown. The current in the circuit is I and the potential difference PD across the external resistor is V. In the equation, E minus V equals to ER, what does the term E minus V represent? Okay, so if you were to apply Kirchhoff's second law for this one, where we tell you that sum of EMF is equals to the sum of PD. So over here, we would have E equals to V plus with VR. Okay, this one here is VR. This one here is V. So VR itself is actually the current times with the internal resistance. So this one is V plus IR. Okay, so the question is asking, what does E minus V equals to ER represent? E minus V is equals to IR. This is the resulting equation. All right. So this IR here, if you were to trace it back, is actually this one, which is this PD here. This part here is actually your voltage loss due to internal resistance. Okay. So, and then when you're talking about voltage is actually voltage. The definition of voltage, the general definition of voltage was just simply W over Q. In other words, energy per unit charge. Okay. So what does the term EV represent? EV is actually voltage loss. Okay, EV is actually voltage loss. So when you relate it to voltage, it's actually something energy per unit charge. So your answer here should be electrical energy per unit charge loss in the cell. This one should be the correct one. Electrical energy per unit charge loss in the complete circuit. No. Energy per unit charge loss in the connecting wire. No. Energy per unit charge loss in the external resistor. This one is also wrong. Okay, so the correct answer is electrical energy per unit charge loss in the cell. This one itself is already voltage loss in the cell. Okay, so answer for this is C. Sorry, answer for this is A. Okay, so that one is all right. Then after that, we move on to page 1, question 36. Okay, so it's again on internal resistance. Have a look at page 1. Okay, so you have a battery of EMF E internal resistance R that's connected in series with a variable external resistor. So the diagram that you have here is kind of similar to the one that you just did, just that rather than a fixed resistor, you have a variable resistor. They tell you that the value of the external resistance R is slowly increased from 0. Which statement here is correct? Okay, so when it comes to this one, you can think of it in 2 ways right now. The first one is this one. Same thing as before, you apply Kirchhoff's second law for this entire loop. E is equals to V capital R plus V small r. Okay, so right now, what we can say from here is this. VR is E minus VR. Okay, right. The first thing to note from here is basically this. Maybe I should write this. When R increases, total resistance increase. Therefore, current decrease. This one is number one. Okay, number two is the voltage loss equals to I small r. When I drops, voltage loss drops. Maybe I need to highlight this so that it's easier to see. Okay, maybe I use pink color, maybe slightly better, I think. Okay, so if you're talking about the voltage loss is current times with the internal resistance. Since current is dropping, the voltage loss is dropping. Okay, then after that, if I were to apply Kirchhoff's second law, E is equals to the voltage across the external resistor plus with the voltage across the internal resistor. I'm gonna get that expression there. So I'm interested to know what is the voltage across the external resistor, the big R here. So the voltage across the external resistor is EMF minus voltage loss. So this one here, you can see that I already found out that VR is dropping. So VR drops, VR increases. So please be careful about the different R's here. This one is internal resistance. This one is external resistance. Okay, so when the voltage across my internal resistance drop, the voltage across my external resistor increases. Maybe it's better if I just write it better like this. PD across internal resistance drop, PD across external resistance increase. Okay, so these are basically what you can see. So you look at this one, the answer choices A and B. They tell you PD across external resistor decreases. This one you already found out is increasing, so this is wrong. The PD across internal resistance increases. This one you already also found out is supposed to decrease. So this one is also wrong. Okay. Then after that comes the part where they talk about power dissipated in small r, power dissipated in big R. So if you have actually watched that lesson on internal resistance, one of the pre-recorded lessons on internal resistance that I did before this, if you refer back to one specific portion in the notes, which was this one, under page 18, I mentioned that when you have something with internal resistance and then you try to increase the resistance R, okay, you try to increase the resistance of the external resistor R, the power dissipated in that resistor would actually vary like this graph here. Okay, I think I showed something like a derivation inside the recorded lesson, but the derivation is actually not required as part of your syllabus. The only thing you need to remember from here is that whenever they ask you about power dissipation in a resistor, external resistor, and then there's internal resistance involved with the cell, your graph is always going to look like this. Okay, so just remember this, you know, power dissipation in external resistor R will always give you this graph shape. So the power with respect to R will always give you this particular graph shape, where we tell you maximum power is dissipated when your external resistance is the same as your internal resistance. Okay, so this is the shape that you need to remember. The derivation, why, how it came to that, that one is really not required in your syllabus, so I'll probably not do anything about that. Okay, so you look back at C, The power dissipated in R increases and then decreases. The power dissipated in R, the big R, increases and then decreases. This one here is for the big R, okay? Is for the external resistor, not internal resistor. So C is also out. A and B just now I mentioned is out. So the D is probably the only answer left. So is it correct? It is correct because power dissipated in capital R increase and then decrease. So you see this one is actually describing this graph. Power dissipated increase and then it decreases. So yeah, it's correct. So this one is answer D. Okay. So that one is okay. That one is internal resistance. Okay, then after that we go to page 20, page 15. Internal resistance again, just to get things properly sorted out. Okay, have a look at page 15. Right. So this one is November 15 P42. Sorry, P21. November 15 P21. So let's clean it out. Number 15 P21. Question 6, the last one. Okay, right. Define the EMF of a battery. Okay, so this one they ask you to define the EMF of a battery. Okay, now this one they specifically mentioned the EMF is defined for what object? For a battery. If you refer to the notes last time when we talked about what was EMF, wait, let me just open out the notes. That one will be under current of electricity. Okay, so if you refer back to the current electricity chapter notes, last time in the notes it was EMF was defined as other forms of energy converted into electrical energy per unit charge, right? So this one was other forms of energy converted into electrical energy per unit charge. This one is actually a general definition of what EMF is. Okay, but when you look at your current question right now, this one, the November 15 P21, page 15, they are telling you to define it for a battery. So if you had just followed the definition in the notes where you say is other forms of energy converted into electrical per unit charge, this one will be wrong. Because this one, other forms of energy into electrical energy is actually a general definition of EMF. But since they mentioned battery here, you need to give them a very specific definition of the EMF. For a battery, the energy that it has is specifically chemical energy. Okay, not other forms of energy, it's chemical energy. So your definition of EMF must be chemical energy converted to electrical energy per unit charge. Okay. So I think I wrote here already. Other forms of energy converted to electrical per unit charge is wrong. It has to relate to the battery. The battery doesn't store any other forms of energy. It stores specifically chemical energy. So be mindful about this whenever you're asked to define something. Okay, so this one is all right. Then after that, you look at part B. You have a battery of EMF 6 volts and internal resistance 0.5 ohm connected in series with two resistors X and Y as shown in figure 16.1. The resistance of X is 4 ohm and the resistance of Y is 12 ohms. Find out the current in the circuit. Now this one is just a very simple calculation where you can just apply Kirchhoff's second law over here, where you say that sum of EMF is equals to sum of PD. This is from K2 law. Okay, EMF will just be E. Then this one will just be IR. Maybe I just write it down properly. E is equals to Vx plus Vy plus V small r. This one will be IRx plus IRy plus IR itself. The same current will be flowing through your system. This one is a series circuit, so same current flows through. Okay, that's why here you see it's all I, and I. This one can be simplified to this now, where we tell you E is I bracket Rx plus Ry plus R. So you know every values inside except I. That is what you want to find. So you just type everything in and you get your answer as 0.364 ampere. Okay, this is the easy part for 2 marks. Okay, then from there, we move to the next part. All right, okay, then we move to the next part, which talks about terminal PD. Okay, so we move to the next part, which talks about terminal PD. Now, terminal PD across battery, this one they give you the specific term, the terminal PD across the battery. Okay, now whenever you hear mention of terminal PD across the battery, it's kind of like the resultant PD across battery or total PD for external circuit. All right, this one I kind of mentioned it already in the recorded lesson. If you look at the DC circuits notes for page, which page already? Page 7 and 8. Okay, so I explained the terminal PD portion from the notes there. I mentioned towards the end there that terminal PD is actually just the net PD across the cell after you take into account internal resistance, where it's actually your EMF minus voltage loss. Okay, at the same time, terminal PD can also be thought of as your PD across your external circuit after you consider voltage loss due to internal resistance. Okay, so it can mean two different things. Either it's the net PD across the battery or the PD across your external resistance. Okay, PD across your external circuit. So I mentioned to you this little diagram here that you have, where you connect your voltmeter here to measure the net PD across your battery. You can actually think of it as, what if you were to shift this point to here? And then what if you were to shift this point to here? Okay, the appearance of your circuit will now look like this now. Okay, where your voltmeter is actually across here. So this voltmeter will actually be measuring the net PD across the battery or cell. It will also be measuring the total PD across your external circuit. Okay, so that's why we say it has two meanings there. Either is the net PD across your battery or your total PD across your external circuit. All right, so there are two ways to go about this when you want to find the terminal PD. So you refer to the notes, if you refer back to that question under page 15, if I'm not mistaken. So you want to find the terminal potential difference across the battery. You could have gone about it in two ways. You can just say your terminal PD is actually your EMF minus voltage loss. EMF minus voltage loss. Voltage loss is current times the internal resistance. You get 6 minus 0.364 times 0.5, giving you 5.81 volts. Okay, so this is your terminal PD. This one is based on the concept of net PD across cell. Now, you can also, as I mentioned, find the terminal PD by considering the total PD across your external circuit. So right now, if you were to think about the circuit right now, this green highlighted portion here is actually your external circuit. This is your external circuit. This blue colored highlighted portion here is basically your cell. All right. So your terminal PD is the total PD across your external circuit, which is the green colored portion that I highlighted here. So your terminal PD, if it's the total PD across your external circuit, the PD across the external circuit will just be Vx and Vy. So it's Vx plus Vy. Okay, that's why there's another different method here. When you want to find the terminal PD, you sum out the PD across X and Y. So terminal PD is I times Rx plus Ry. Take the current, multiply with resistance X plus with resistance Y. You're going to get the answer as 5.82 volts. Okay, so this one is based on the consideration that this one is total PD across external circuit, right? So this is terminal PD from two different criteria. Okay, so that one is okay. Then we go move on to the next part. Okay, so let me know if I'm going too fast, then I'll just slow down a little. Okay, so if you're okay with this, then look at part C. Part C, they tell you a resistor Z is now connected in parallel with resistor Y in the circuit in B. The new arrangement is shown in figure 6.2. Resistor Y is made of wire length L and diameter D. Resistor Z is made of wire from the same material as Y. Length of wire Z is L over 2 and the diameter is D over 2. Calculate the resistance R of the combination of resistors X and Y. Okay, so this one, your resistor Y now has another resistor Z connected right across it. They want you to find out the resistance or combination of resistors X and Y. Basically, they want you to find what is this resistance, which is a parallel connection, right? So you want to find the resistance, obviously it will be 1 over RT equals to 1 over RY plus 1 over RZ. Right? Maybe this one I just write it properly. 1 over RT is equals to 1 over RY plus 1 over RZ. Now you have a problem here because you know, while you know what is RY, you do not know what is RZ. The question never really did mention to you what is RZ. You have to go and find out what is RZ. Okay. I think it is yeah. Okay. So you have to specifically mention find out what is RZ. So how do you go about doing that? You see, they give you some information about length, diameter, and it's mentioned about same material. So intuitively, you should know that you need to use this equation. R is equals to rho L over A. Okay, you will need to use the equation R is rho L over A. R is rho L over A. Because you got mentioned on diameter, the area please change to pi over 4d squared. Now, because this thing is mentioned to be same material, Y and Z are same material, you can say that same resistivity rho. Okay, so this one is constant, this one is constant. Therefore, R is proportional to L over D squared. So Rz to Ry is Lz to Ly dy squared to dz squared. Because this one is in essence the same as Rz to Ry equals to Lz to dy square over Ly divided by dy square. This one is z, sorry. Okay. So you get this. Then from there you just sub everything in. You know what is the value of Ry? It is 12. And then what is the values of the lengths? So resistor Z is, sorry, resistor Y, length L, diameter D. So L, diameter D. But YZ is L over 2, D over 2. So this one is L over 2, D over 2. Now I know I wrote here 1 over 4. That's because D over Z squared is the same as 1 over 2 D squared. I actually already squared the half to give me a quarter here, 1 over 4. Okay. Then after that, you will get the answer as 24 ohms, right? There's a typo error for the workings here. This one is not RY, this one is RZ. Okay, so there's a typo error here. This is RZ. So from there, you already know the RZ is 24 ohm. You just sub in 1 over 24. You get your answer for total resistance for the parallel connection as 8 ohms. Okay, so that one is okay. No, 15 to 1. Okay, so you'll get the resistance R as 8. All right. So now that one is okay. Then we go on to the last part, which is the state and explain question. Now, state is explain the effect on terminal PD across your battery. Once you go and add another resistor here. Okay. So you could kind of think of it as this. By now, terminal PD, based on what I just explained to you, terminal PD is net PD across cell. One way of finding it is V is EMF minus voltage loss. And voltage loss in turn is equals to current times R. Okay. So now, you see, once I go and add my resistors in parallel, the resistance of the circuit is less. So my current becomes larger. The voltage loss in battery is greater, therefore terminal PD is less low. So how do I go about in doing that? The line of reasoning looks like this now. So now you should recall this one here. This one is 24 ohms, right? All right. This portion here just now before was 12 ohms. Now this one is 12 ohms plus with 24 ohms. This is the after case. Now your total resistance here is actually 8 ohm. You already found out already. Before this it was 12. Now it's 8. Notice that your total resistance has actually decreased from 12 ohms to 8 ohms. Okay. So just think of it. One thing I should probably just mention to you here is that when circuit is made into a parallel connection, the resistance tends to decrease. Okay, so this one, just bear this in mind. In general, when we try to make a circuit into a parallel connection, we go and introduce a parallel connection like the ones we do here, your resistance will actually tend to decrease. Whenever you're trying to make some part of your circuit into a parallel connection, almost always your resistance will tend to drop. Okay, so your case here is that this one was originally in series. It's just one single resistor, but now you go and add a parallel connection. Your resistance for the new parallel connection here is actually going to be less than before. You see here, it dropped from 12 to 8. Okay, so from there, if you were to try and consider the whole circuit here, you consider the entire circuit there, your total resistance actually is now dropping because this portion itself has already dropped in resistance. So total resistance drop, current increase. And then voltage loss is IR. Is IR. So from here, if I increase, that means V increase, no? So this one is what we mean by voltage loss increase, no? Then after that, your terminal PD is V equals to E minus VR. So if VR increase, your V will drop. Okay, so that's what this little statement here actually meant. The resistance of the circuit is now less, thus your current becomes larger. Your voltage loss is greater, therefore terminal PD will be less. Okay, so this is one part. Right, next one that I'll go through with you is page 26. All right, so next one is page 26. This one ought to be something a bit different already. Okay, so let's have a look at page 26. DC circuits. Page 26. Miss. Page 26 is not that. Okay, now just have a look at page 26. Now we'll just go through this really quickly because this one is something like just a simple exercise in terminal PD. Okay, so page 26, question 6B, I think 7B. Okay, right, question 7. Oh, sorry, question 7. Right. So look at that question there. Right, so you have a battery of EMF 9 volts and internal resistance 0.25 ohm that's connected in series with two identical resistors X and then resistor Y. As shown, the resistance of each resistor X is 0.15. The resistance resistor Y is 2.7 ohm. Show that the current in the circuit is 2.8 amps. This one not that big of an issue. It's kind of similar to the method that I just showed you, where we tell you that sum of EMF is equal to sum of PD. So E is I times Rx plus Ry plus Rx plus internal resistance. This one here, without the convention, this one should have been sum of EMF equals sum of PD. Okay. So this one is still seeing current flowing through all the resistors. That's why all of them are considered to be I. So add everything in, you can get the answer as 2.8 ampere. Okay, so that one is okay. Now, then after that, they ask you to calculate the potential difference across the battery. Calculate potential difference across the battery. This one here, you should be able to identify it as being your terminal PD. This one is asking you about your terminal PD. PD across your battery. So this is terminal PD. They're asking for your net PD across battery after taking into account voltage loss. So as I mentioned to you, there are actually two ways to go about it. Either you just take EMF minus voltage loss. Voltage loss is I times R. You get 9 minus 2.77 times with 0.25, giving you 8.31 volts. Or your terminal PD is sum of PD across external circuit, which is Vx plus Vy plus Vx, which is basically what this one is trying to do. Okay, so this one is terminal PD. Okay, so this one, I think terminal PD, you should have a good idea of what it is already. Okay, so that's one, okay, no issues. Then I move on to some slightly more difficult internal resistance example. Okay, wait, internal resistance 46, question 34. Wait, why do I have question 34 here, but oh, 46, question 34. Sorry, please have a look at page 46, question 34. Okay. Right, now you have a simple circuit that comprises of source of EMF connected to a load. How does the output power P of the source depends on the internal resistance R of the source and resistance R of the load? This is somewhat related to this one. Okay, it's somewhat related to this one. Okay, so your P actually depends on both small r and big R. That is supposed to be the answer here, but why? Let me just undo what I just did. Okay, so let's have a look at this one. When they describe that situation here, you can just think of it as a circuit like this, where we tell you this one is your circuit with internal resistance R. This is E, this is R. This one is your internal resistance. And then this one is connected to a load R. Your load is actually a resistor R. Okay. So if I try to look at this case right now, I know I have current I. If I'm talking about power dissipated in resistor R, it will be I squared times R. Okay, so this one is what I have in the first place. All right, but let me just redo this one properly for you. So here, if say I go and apply Kirchhoff's second law for this loop here, sum of EMF equals to sum of PD. E is V capital R plus V small r. This one will be I R plus R. I will be E over R plus R. Okay, this is your current flowing through your circuit. So second thing I want to do is this. Power dissipated in R is P equals to I squared R. So you already found out what is the current here. This one will just be E over R plus R times, remember to square the term, times with R. Okay, so is this expression here for power that will give you that graph that that we went through earlier, the ones where we tell you that the power dissipated with respect to the resistance R will always look like this shape, where R is equals to small r, that one will give you P max. Okay, This equation gives you this. All right. How you're going to get this shape? This one has something to do with what you learn in maths, where you need to do dp over dr equals to 0, then d square, dp square over dr square, d square p over dr square, d square p over dr square. See whether it's more than 0 or less than 0. You will find that it's actually less than 0. So therefore, this one is max point. Then this one is to find stationary point. Okay, so you learned this in maths before, how you go and predict the shape of a graph, where is the stationary point, whether the graph is going to be a maximum point or minimum point. You have to do differentiation. You do it the first time, you do it the second time. So once you do this, that's how you got this shape. But as I mentioned to you, this one is not really required in your syllabus. You are not required to know until that extent. You just need to know the shape of the graph. That's all. Okay, so back to this question here, they are asking you, how does the output power of the source depends on the internal resistance R of the source and resistance R of the load? P actually depends on big R and small r. Okay, it depends on both small r and big R. Okay, now I know they tell you that this is the output power of the source. This is actually the same as power dissipated in R. Okay, so you may be thinking right now, here the question is saying output power of the source, but you think about it, whatever output power you have from the source is going to be dissipated in the resistor in the first place, or load lah. Okay, it's going to be the power dissipated in the load. So it's basically talking about the same thing, right? So the answer is D. This one is correct, right? So that one is fine. Okay, then I move on to another separate part. Page 32. Okay, this one has internal resistance. Okay, now this one has a combination of a few things. Okay, so can you have a look at page 40? This one is 31, sorry. Have a look at page 31. Okay, so November 16P22. November 16P22. Page 31 of your worksheet. All right, so this one, I'll just clear off everything, and then we just do this one. And this one is page 31. All right, so statewise Kirchhoff's second law. Kirchhoff's second law is just saying that the sum of EMF is equal to the sum of PD around a loop. Or you can just say the statement in red here, total EMF equals to total PD around a closed loop. Okay, the ones that I written here in pencil seems a bit long. If you want to shorten it up, just say this: total EMF equals total PD around a closed circuit or closed loop. You can replace the closed circuit with closed loop. Okay, this one is the shortest possible definition. But when you do your definition of your Kirchhoff's second law, please be mindful to always write this term, total EMF, total PD. Or if you don't want to write total EMF, total PD, just write sum of EMF, sum of PD. Okay, that is the keyword that your examiner wants to look at. You must have the word sum or total of the PD and EMF. If you don't have that wording there, they will mark you as wrong. Okay, so that one is okay. Then we move to part B. Okay, right, so I'll just clear everything here. Okay, now a battery is connected in parallel with two lamps A and B as shown. The battery has EMF 6.8 volts and internal resistance R. The IV characteristics of lamp A and B are shown. This is lamp A and B here. Okay, so the potential difference across the battery terminals is 6 volts. Show that the current in the battery is 0.4 amps. Okay, so they tell you that the potential difference across the battery terminals is 6 volts. This is your terminal PD. Okay, so this one they tell you this one is your terminal PD. So just read this as terminal PD. Okay, which I mentioned to you can mean two things. Net PD cross cell or battery. Sometimes I write cell, sometimes I write battery, doesn't matter. Or total PD across external circuit. Right? It simply means these two. They want you to show that the current in the battery is 0.4 amps. Okay. So this 6 volts here, just be careful. This is not EMF. All right, because I have people tell me that this one is EMF. This is not EMF. This is the terminal PD. Okay. Right. So your terminal PD is 6 volts. What this simply means is just this. If you were to connect a voltmeter here and here, like this one is your voltmeter. Connect a voltmeter here. This voltmeter here will be measuring your terminal PD. It is basically telling you that your net PD across your battery is 6.0 volts. It's also telling you your net PD across your external circuit is 6.0 volts. That means this one is 6.0 volts. This one is also 6.0 volts. Okay, that is what you should be able to infer from the circuit. Why is this PD going to be the same as this PD? Is because this one is a parallel connection. Okay, whatever PD you have at the top will be the same as the PD that you have at the bottom. Okay, so that's what you should be able to see. Okay, but now the question wants you to find out what is the current through your battery. That is the main issue here. They want to find out what is the current through your battery. Let's call this current as I. Your current I flows through your battery. It comes over here. Let's just disregard the blue colored line. It comes over here, and then it hits this junction. Once it hits this junction, by Kirchhoff's first law, you know that your current will split up. It becomes IA, it becomes IB. Okay, from K1 law, you would know that I is equals to IA plus IB. This one is the current through your battery. Okay, so you want to find IA and IB. How do you find IA and IB? They've already given you the graphs, IV graphs for filament lamp A and B. So this one you find from graph. Now, because here you already identify that for filament lamp A, you will have PD 6 volts. Filament lamp B, you also have 6 volts. So you find from graph when V is equals to 6.0 volts. Okay, that's the reason why you have that graph there, right? So you go and find from the graph, you find from your graph 6 volts, which is going to be this line here. And then you find out what's the corresponding current for filament lamp A and B. So for filament lamp A, you're going to get 0.14 ampere. Filament lamp B, you're going to get 0.26 ampere. This is the current through lamps A and B when their PD is 6 volts. Okay, so 0.14, 0.26. So from there, you just add them up. Okay, so your working will look like this. When B is 6, IA 0.14, IB is 0.26. So I is IA plus IB. Add them up, you're going to get the answer 0.4 amps. Okay. Okay, so that one is okay. Then after that, they ask you calculate out the internal resistance R of the battery. Okay, so calculate out the internal resistance R of the battery. This one shouldn't be that big of an issue. If you want to calculate out the internal resistance R of the battery, you can again look back at this one. Okay, you can again look back at this one here. You can actually just say that your terminal PD V is, I'm talking about terminal PD here now, all right? You can just say that your terminal PD is actually V equals to EMF minus voltage loss. Is E minus with I times R. Your terminal PD, you know it at 6 volts. Your EMF, you know it at 6.8 volts. Your current, you already found out at 0.4. So you can find out what is R. Your R is just going to be some value there, which is 2.0 ohm. Okay, 2.0 ohm. Okay, that's one thing you can do. Right, from there is okay. Now, some people may do it a bit differently. Okay, the other thing I'll show you is how they do it. They go and just apply Kirchhoff's second law, which will actually give you back the same answer. Let me find a suitable color. Okay, I'll use orange. If let's just say you apply Kirchhoff's second law for this loop, just this loop. Okay, apply Kirchhoff's second law for this loop. So from K2 law, you're gonna get EMF E equals to voltage loss plus with voltage across A. So this voltage loss is I times current times your internal resistance plus voltage across A, then equals to E. So E is 6.8, current is 0.4 times R, plus with voltage across A, which you already know was 6. See this working here is actually going to be the same as this one here. You're going to get back the same answer as R equals to 2.0 ohm. Okay, so it doesn't matter which one you want to use. Either you go and use the concept of terminal PD straight, or either you use Kirchhoff's second law, apply to one loop in your circuit, you're going to get back the same answer. Okay, it doesn't matter which one you use. Just a matter of which are you more comfortable with, that's all. Right? Okay, so that one is okay. Then we move on to the last part of the question. Okay, we move on to the last part of the question. Okay, so for the last part of the question, they tell you determine the ratio resistance of lamp A to resistance of lamp B. Okay, so what you can do is that V is equals to IR applied to lamp A and lamp B. Because the voltmeter, because the lamps are connected in parallel, they have same PD. Just now I mentioned that already. So that's why I can say that V is constant. All right. So therefore, R is inversely proportional to I. I want to find out the resistance. I'm just applying V equals to IR for lamp A and lamp B, but I know that because they're connected in parallel, they must have same PD. Okay. So V is constant, R is inversely proportional to I. I can then work out an equation saying that RA to RB is the same as IB to IA, because this one is RA over RB equals to 1 over IA over 1 over IB. IA, IB, I already found out from the previous equation, from the previous question. So I can just sub the values in straight. Then I get the value as 1.86. All right.